Hello, we're going to look at photosynthesis and some data that's associated. So let's look at the first half. This would be the classic, pondweed in water and measuring the volume of oxygen that's produced. So we are varying the intensity of light. The lighter the bulb, the greater the intensity. So it's not surprising that when there's a high intensity of light, that there's a lot of oxygen produced. When there's no light, there's no oxygen produced. Um, so let's look at our graph first of all. So I plotted the data, and it's like, what line should I draw on this graph? Well, a lot of people will do this wrong line. They'll go, oh, that is miles off the point. So the problem point is here at the bottom. I can't go to zero. Zero does not equal zero. Okay, let me just undo that line. The line I would draw on this is that I'd be going up here like that, and then I'd be going across. Okay, because I don't know what light intensity gives me zero bubbles. Because if I just give a little bit of light, that might not be enough light for the pondweed to actually be a net producer of oxygen. Remember, it's using oxygen as well, and it's using that in respiration. Okay, so let's do question 2 first, because it kind of makes sense to do so. Oh, well, I'm here, as I increase light intensity, light's the limiting factor, light's the limiting factor, light's not becoming the limiting factor, and now there's something else is limiting the rate of photosynthesis here, the oxygen produced per minute per gram of pondweed. So yeah, if I just extrapolate this down here, so that there, so about about 3, so 3K lux, that's the light intensity I would need to get to the light compensation point. So yeah, anything more than 3, there'll be a net production of oxygen, and really you could even extend this axis down here, and you could extend this further down here as well, and you could find out the volume of oxygen probably used in respiration is going to be this much here. Yeah, so when there's no light, it'll only be using oxygen, and therefore you can extrapolate down. So that point there, let's do it in red so you can see, that is the light compensation point. Yeah, and you're often trying to find it out, hence you will do an experiment where you're varying the light intensity, and then you extrapolate your line down again. I should have gone through these units a bit better as well. So yeah, so we're measuring millimeters cubed of oxygen per minute per gram of pondweed. So on number 1, it says I collected 3.2 millilitres of oxygen in an hour from 36 grams. So I've got 32 mil to sort out, I've got an hour to sort out, and I've got 36 grams. So I tend to just write this out first of all, 3.2 millilitres per hour per 36 grams. Okay, so that's the units I've got. So let's change the millilitres first. Well, 1 ml is the same as 1 cm cubed. And therefore 1 cm cubed equals 1,000 millimeters cubed, because 1 centimeter is 10 millimeters. 1 centimeters cubed is 1 by 1 by 1, so I need to do 10 by 10 by 10. So therefore, this is now 3,200 millimeters cubed per hour per 36 grams. So now let's go into per minute, because I need to get this in the same units as I've got over here. So let's get into per minute. So I need to divide by 60. Do I multiply all times by 60? Well, it's going to produce less gas in a minute than it would in an hour. So I'm going to divide by 60. So that comes in at that comes in at 53, isn't it? 53.3. I haven't got my calculator, so I'm just trying to read off my scrappy writing. Yeah, millimeters cubed per minute per 36 grams. Now, if I've got 36 grams of pondweed, that's going to make more oxygen than just 1 gram of pondweed. So I'm going to have to divide by 36 now to get it into per gram. So that comes in at 1.48. And now I am in the correct unit, millimeters cubed per minute per gram. So, you know, it's about 1.5. So I go to my graph, I find 1.5 in terms of the oxygen produced. Again, I'm on a screen here, so forgive me for the wobbly line. And then I come down from the line of best fit. And yeah, that's going to be 6.5. So a light of 6.5 kilolux would give me the rate of 3.2 milliliters of oxygen an hour from a 36 gram piece of pondweed. But yeah, it's the classic kind of unit conversion. Just try and do it methodically. You know, put them underneath each other in order to show the steps: step 1, step 2, step 3, step 4, and you know, like underline your final answer. Again, they'll often say answer here. So yeah, my answer would be 6.5, and it'd be a hard question. That to do all of that conversion and read from a graph as well, but not beyond. Yeah. So that's compensation point. Next is, I thought we'd have a look at a graph where we're going to look at the amounts of or the relative amounts of two of the kind of compounds in photosynthesis. So we're going to look at GP and RUBP, and we're going to kind of build up a graph of what it's going to look like. So anytime I get a question about the light independent reaction or light independent stage or Calvin cycle, all those three are the same thing, I always draw out a quick Calvin cycle. It's like, can you draw out a quick Calvin cycle? So CO2 comes in, and that's going to react with RUBP, and I make 2 times GP. Again, I have to name these if I can't just, if it says, you know, name the compound that reacts with carbon dioxide in Calvin cycle, I would have to say ribulose bisphosphate. And then I get 2 times TP, and then this goes back to there, and then that's 5/6 of the time, and then 1/6 of the time it comes over here into glucose. You know, so that's my quick step, and then I always put it's this step here that this is a step that requires light. Yeah, so this needs ATP, and it needs NADPH2, and they're from the light dependent reaction. Okay, yeah, because I need to oxidize. I oxidize NADPH into NADP, and I therefore reduce GP into TP, requiring the energy from ATP. Okay, so we're going to plot these two. I'm going to do GP in red, and we'll do RUBP in blue. Okay. Now, first of all, GP in the light when it's carbon dioxide. So this is a plant zipping along doing photosynthesis, both stages. So RUBP, I'm going to put at 1 unit. There it goes. So it's bumbling along, and it's a straight line. And they'll ask about why it's a straight line. Whereas GP, I'm going to put at 2 units. So question 1, which they'll ask, is why is it not changing? And this is when we say, well, it's part of a cycle, and therefore, as fast as it's being made, it is being used. So it's being made and used at the same rate. That's why these are horizontal lines. They are not changing. Yeah, it's in a constant light, constant CO2 environment. Why is there twice as much GP as RUBP? Well, because every RUBP, when we carboxylate RUBP, remember that's a 5 carbon. This is 2 times 3 carbons, but it's 1 RUBP gives me 2 GP, hence why it goes 1 and 2. Right, now let's pop it into the light. Sorry, from the light into the dark, and we're maintaining carbon dioxide. So we're going to go into this time period now. So I've turned the light off, so it can no longer do the light dependent reaction. It's going to run out of ATP and NADPH. Okay, it's still got CO2 though, so it can still do this step here from RUBP to GP. So GP is still made. However, GP cannot be converted into TP. That can't be, and therefore I'm going to run out of TP to regenerate into RUBP. So this will just mean that my red line is going to go up and my blue line is going to go down. I've just kind of gone over the line slightly. Let me just correct that. There we go. Then I'm going to put them back into the light. So now I've got lots of GP, but not much RUBP. Note the slope of this line is steeper than this because every RUBP becomes 2 GP. So yeah, so if there's more GP, then it's more likely to be converted into TP. Then RUBP is likely to be converted into GP. There's enzymes involved, so chances of collisions of things. So over time, this is going to kind of regulate, like self-regulate back to 1 and 2. So it will, just by chance of collisions and things, it's going to come back to. Again, it depends on the time period, but yeah, it's all explainable, like I'm saying. So that's the same as it was. Oops, sorry. That's the same as it. So I've got light in plus CO2, dark plus CO2. Then I've gone back into light again. So I'm back to where I was at the start, in effect. Now we're going to get rid of CO2. So if we've got rid of CO2, it can't do this step, which means that RUB can't be converted into GP. So GP is going to be slowly used up because GP can be converted into RUBP because I've got light, therefore I've got ATP and NADPH. So this is where we get the classic kind of crossover graph where this comes down and my blue line goes up. Yeah, so we get that classic crossover line, and therefore this was like proof of how photosynthesis worked in terms of like building up the knowledge of the Calvin cycle. And they did like Calvin's lollipop experiment as well, so they could prove that GP was made first, TP second, RUBP third, and glucose fourth when they did all that radioactive carbon dioxide, radioactive carbon in carbon dioxide experiments and chromatography. So that's it. Yeah, maybe you can write some, what we've done into detail. Just call this like section 1, section 2, section 3. Kind of, I probably ignore that really because it's just bringing it back to normal again. But yeah, section 4. So 1, 2, and 4 are the important bits, but it all relates back to understanding Calvin cycle, the light independent reaction, and then just thinking it through. So yeah, why is it horizontal at the start? Why is there twice as much GP? And then why does GP increase? And RUBP decrease in that one? And why is it the opposite in this one? And I shall stop there. Wonderful. Short one.